This video presents multiple comparisons and then also some general information on carrying out statistical significance tests and something that is sometimes called fishing. So we begin with multiple comparisons. Multiple comparisons are conducted only when the F from ANOVA is statistically significant. So a statistically significant F in ANOVA conveys that at least one pair of means differs statistically. The next step is to identify which particular pairs differ. And that's what we're going to see multiple comparisons are designed to do. Now, one approach for identifying which pairs differ would be to conduct multiple independent samples t-tests. Now, one disadvantage of doing so is that the number of tests, in other words, the number of comparisons between means, increases rapidly with the number of groups. The number of different independent samples t-tests that are necessary to compare all pairs of means equals j times j minus 1 divided by 2, where j is the number of groups. So you can see that, for instance, if we had 5 groups, we would need to conduct 10 different t-tests, or 10 different comparisons. Now, recall that a type 1 error is the error of rejecting a true null. The probability of type 1 error given a true null equals alpha. For instance, at the 0.05 level, the probability of rejecting a true null equals 0.05. Alpha is the same thing as the probability connected with the selected significance level. Now, the probability of type 1 error applies to each individual test or comparison. So, if you are carrying out a series of comparisons, the probability of a type 1 error for at least one comparison in the series is greater than is that for any single comparison. Presume again that we have 5 groups. In this case, we need to carry out 10 comparisons. Now let's presume that the null is true for each comparison. Now, for any given comparison, for any individual test, the probability of type 1 error is 0.05. But for the full series of 10 comparisons, the probability of committing at least one type 1 error, that is to say a type 1 error on any one of the 10 tests, or perhaps it could be on 2 or 3 of them, that probability equals about 0.40. So this probability is considerably greater than the probability of committing an error on one given particular test. So if we conduct multiple t-tests and just look at the significance level of each of these different tests, the probability of making at least one type 1 error will exceed the chosen significance level. That probability will be greater than alpha. So multiple comparison procedures deal with this problem. Basically, and oversimplifying to some degree, multiple comparison procedures adjust the risk of type 1 errors so that this risk applies to the whole series of comparisons being carried out rather than to each particular one. For instance, in our example, we could set the risk of type 1 error to 0.05 to apply to the whole series of 10 different comparisons that would be conducted between sample means in our situation involving 5 groups. Software packages carry out multiple comparisons. There are many different multiple comparison procedures. Each one adjusts risk in a slightly different way, and it's beyond our scope to go too much into which procedure you should use in one situation or another. But for instance, the SNK, Tukey, and Bonferroni procedures are well-known multiple comparison procedures that you might consider using. Well, let's build on the ideas that we've developed for multiple comparisons, because these ideas apply to significance tests as well. So suppose that you are carrying out a series of significance tests. Suppose that you have a study and, for instance, you're carrying out 15 tests. And suppose that you set alpha to 0.05 for each one. The probability that you will make a type 1 error for at least one test that you carry out is greater than that for any single test. So if we presume the null to be true for any given single test that you carry out, the probability of type 1 error equals alpha, the selected significance level. But the probability of at least one type 1 error being committed for the entire series of tests is greater than this. So, for instance, suppose that we had 5 independent variables and 3 dependent variables. Well, there would be 15 different combinations of tests that we could carry out. The significance level, alpha, applies to each test. So if we presume that the null is true for each test and set alpha to 0.05, the probability of rejecting the null on at least one test is greater than 0.05. As a matter of fact, that probability equals about 0.54. So that you can imagine a situation where it is the case that the null is true in each of 15 tests that are carried out. Even though that's so, if you use the 0.05 level, you've got about a 50-50 chance of rejecting the null on at least one of those tests. So the basic message in a research study is that if enough different statistical significance tests are carried out, sooner or later, one or more will achieve a significance. There's a term that's called fishing or statistical fishing, and this refers to conducting many, many tests searching for a significant result. If you conduct enough tests, sooner or later you're going to catch a fish. That is, you're going to find a statistically significant result. The number of tests that are conducted is only part of the problem. Picture yourself as a reader of a journal article. It may be that many, many tests have been conducted, but the results of only a few have been reported. So in other words, the researcher can cherry pick the statistically significant ones and report them. Now, if a particular study involves only a single test, and further, if this test is planned for ahead of time, then the probability of type 1 error, rejecting a true null, that probability is indeed equal to alpha. The alpha level is accurate. In this situation, if you carry out that single statistical significance test, you reject the null, you can indeed be 95% confident that the null is false if alpha is 0.05. Now suppose that a researcher conducts a reasonably small number of tests, and that basically these tests are planned for ahead of time. In such a situation, you, the reader, you can have basic confidence in results. In other words, the tests are reasonably valid and the alpha level is reasonably accurate. But it is the case that because several tests have been conducted, the probability of a type 1 error on at least one of these tests is indeed greater than the selected significance level. So even in this situation, you should have some skepticism about results. Now, if many, many tests are carried out with little guidance from theory, and further, if results are reported selectively, in other words, that any results that are not statistically significant are not reported, you should be very skeptical about results. So in these situations, the probability that at least one type 1 error has been committed is much, much greater than alpha. And I'll try to convey the problem here. It's a very difficult problem, because if, say, 15 or 20 tests are carried out and 2 or 3 are statistically significant, then you look at them and you really don't know whether, this result is significant primarily due to fishing. The researcher has just fished until they found a result and now they're bringing that forward to us, or whether indeed there really is likely a difference at the level of the population. In other words, the alpha level is increased to some unknown amount. So, rather than being, for instance, 95% confident that the null is false, you might be 70 or 80% confident. I mean, it's very, very difficult to untangle this. So you should be alert to the situation where you're reading about many, many, many different statistical significance tests. You should recognize that just by chance, just by the luck of the draw, some tests will achieve significance. So have some strong degree of skepticism in this situation. So perhaps you think I'm going to advise you, do not fish. Well, fishing is indeed problematic, because fish long enough, almost assuredly you'll find some statistically significant results. But there are also dangers of not fishing. That is, to seeing only what theory wants you to see. This is really akin to putting on blinders. Today, computers effortlessly crank out numbers and tests. So, you get too much information, so that's problematic. But on the other hand, it's foolish not to exploit the information in your data and the information that the computer can generate for you. So if you go back to 50 years ago, hand calculations were the norm. It was impossible to fish. In other words, the researcher needed to spend probably long hours carrying out computations and then double-checking them to be sure that mistakes weren't made. More than likely, the researcher had graduate students doing this, but it simply wasn't possible to go fishing and exploring one's data to find interesting analyzing results. By necessity, by the limits of time, you had to stick pretty straightforwardly to your theory and to a limited number of questions. Do some exploring of your data. You'll learn things in that way. Discoveries in science are often made by exploring data rather than by looking blindly at predictions. But I guess here's the flip side. If all that you were to do was to fish, then likely your results will be garbage in and garbage out. And that concludes Chapter 21.